Hello everyone, welcome to the lab 3 of ECE573 Advanced Embedded Logic Design. We'll continue our discussion on the SDSoC and the various pragmas, and in this lab we'll discuss how to implement the matrix multiplication using the SDSoC and how to improve the acceleration factor via FPGA. As discussed in the lab 2, SDSoC allows your C code to be divided between the hardware and software, and the software part is converted into the object code via compiler, while the hardware part is converted into the bitstream via the high-level synthesis and the Vivado design flow. So in the SDSoC flow, you have the three subtools. One is the SDSCC compiler, SDS++ compiler, and then there is a linker, SDS++ linker. SDSCC compiler process the C sources which we add inside the SDSoC and convert them into the object code for execution on the ARM processor of the SoC and RTL code for execution on the PL part of the SoC. So C code marked for the software implementation is compiled using the GCC compiler, while the RTL code is converted into the Verilog and VHDL using the Vivado HLS2. The same is true for the CPP code, where we use the ARM G++ compiler for converting the CPP code into the object code for implementation on the ARM processor of the SoC, and the HLS is used for converting the C code to the Verilog or VHDL code or RTL code for implementation on the FPGA. Then you have the SDS linker, which takes the output of the compiler and the Vivado HLS to create a file which can be used to program the SoC. A linker is called to link the object code generated by the SDSCC compiler or SDS++ compiler, that is GCC and G++ compiler, with inbuilt libraries which we use while writing the C or CP+ code to create the executable file, which is the ELF file. Similarly, for the hardware part, we have the Vivado tool from the Xilinx, which takes the Verilog VHDL code along with the data motion networks, which takes care of the data communication between the PS and PL and create a bitstream via synthesis, placement, and route. So we have majorly two steps: synthesis and implementation. Inside the implementation, we have the map, place, and routing state. After that, we generate the bitstream. Finally, the boot image is created incorporating the executable file and the bitstream using the bootgen utility. So if you have tested your code on the hardware, you will see that there is a boot.bin file is created, which is created using the bitstream, ELF file, and the bootloader inputs. The boot image can be loaded onto the SD card and used to boot the Zynq device. So we get all the files needed for the SD card, we dump them on the SD card, and once after the appropriate jumper setting on the zedboard, your zedboard, when it is restarted, it gets booted using the files available in the SD card. So in case of the SDSoC design flow, we start with the C++ application for a chosen platform, for example, zedboard, ZC706 board or ZC72 board, whichever is available to you. Then you do the profiling of the application. That means you decide which is the complex part in your algorithm and which needs to be implemented on the hardware. Then you select the particular function, you do the performance analysis. If the performance analysis is not as per the desired expectation, you add the pragmas for the hardware function as well as for the communication between the hardware and software. And as you repeat this process multiple times to get the desired performance. Once you get the desired performance, then you execute on the hardware on the board. You test it on the board. If everything is working, you generate the final files and then you copy them into the SD card and you deploy your applications. So here the pragmas are used which act as a special directives that can be inserted into your C code or CPP code to guide the system compiler. Okay. So in the SDSoC, you can control the system generation process by structuring the hardware functions by using the Vivado HLS pragmas and calls to the functions by using the SDS pragmas, which controls the data motion networks so that you can have balance the communication between the PS and PL along with the computation inside the PL. So you need to make sure that your implementation on the PL is optimized. At the same times, there is not the communication between the PS and PL is efficient so that the communication time is sufficiently smaller than the computation time. If the communication time is significantly higher than the computation time, then you will not get the desired performance as we have seen in the vector addition or vector multiplication example where the PS processor is faster than the PL because the computation is easy, but the communication between the PS and PL is time consuming. Okay, so the pragmas are used to guide the compiler, and that's why the in-depth understanding about the pragmas is important. For example, there are two types of pragmas. One is the SDS pragmas, which are used for the data motion networks and how the PS communicates with the hardware, and then others are the HLS pragmas, which are used to optimize the hardware. So in this lab, we are going to focus on the pipeline pragmas and the array partition pragmas for our matrix multiplication operation. Over the semester, we'll learn about the rest of the pragmas as and when needed, but you can also go through the pragmas and learn some of them on your own. So we'll start with the HLS pipeline pragma. So what is pipeline? So as discussed in the previous lab, pipelining allows the operation to happen concurrently. Okay. For example, in case of the previous lab, we did the vector multiplication. So we were reading the a of 0, b of 0, then we are doing the multiplication of a of 0, b of 0, and then we are storing the value output of the multiplication in the memory. So without waiting for the complete operation, we can read the next value a of 1 and b of 1 so that the multiplications can be initiated immediately. Okay. So the pipelining allows the operation to happen concurrently. That means each execution state doesn't have to complete all the operation before it begins the next operation. Okay. For example, here you can see that we have the void function where you are doing the three tasks: read operation, compute operation, and write operation. Okay. So in the conventional operation, for example, when you implement this on the processor, you first perform read operation, then you perform the compute operation, and then you perform the write operation. Okay. And then you start the next execution of the function read and compute and write. So without pipelining, you can see that you are reading the new input at every 3 clock cycle. That means your initiation interval is 3 clock cycle, and you are outputting the value after 2 clock cycle. Like that means your latency is 2 clock cycle. Okay, so your initiation interval is 3 and the latency is a 2 clock cycle, means your data is available at the third clock cycle. Okay, now when we do the pipelining, so what do you mean by pipelining? I am in after I complete the first read operation, I am immediately beginning the read operation of the next function execution. Okay, so that means at every clock cycle I am doing the new read operation. So that means initiation interval is only 1 clock cycle. Is there any change in the latency? No, the output latency remains the same. Okay, so in the pipelining, you can see that I am utilizing my hardware more efficiently. In the previous one, you can see that my read unit is utilized at every third clock cycle. While in case of the second with pipelining, I'm using my read unit at every clock cycle. So my utilization of the hardware is improved. The ideal time of the hardware is reduced. Okay, so there is a difference between the parallel execution and pipelining. Here I am not doing the parallel execution by using the additional resources. My number of resources are remains the same. I'm increasing the utilization of those resources. So pipelining can be applied to the functions or to the loops as well. Okay, depending upon the how you want to enable the concurrent operation, you can apply the pipelining to the functions as well as loops. For example, this is the function where you have the for loop, and the for loop has the 3 iterations. Again, we take the read, compute and the write. When you don't pipeline this for loop, you can see that you will your iteration of the one iteration will take 3 clock cycle, and since you have 3 iterations, you will take total 9 clock cycle. That means at the 9th clock cycle you are sending the data for the write operation. Now, by using the loop pipelining, what you want to do, you want to start the next iteration of the loop as early as possible. Here I am starting the next iteration of the loop after 3 clock cycle. Okay, so here you can see that my initiation interval of the loop is cycle, and it takes total 8 clock cycles before the last output write is performed. Now coming back to the pipelining version. So in the pipelining version, you can see that I'm starting the each iteration of the loop at new every clock cycle. So that means I'm reading the new samples at every clock cycle. So my initiation interval is 1. And you can see that my loop execution is completed at the end of the 4th clock cycle. By the 5th clock cycle, I'm performing the write operation. So you can see that here I'm able to improve the initiation interval as well as the latency of the loop. Okay. Did I use the additional hardware? No, I'm still using the one read hardware, one comparator hardware, and one write hardware. So it is just I'm improving the utilization rate of those hardware. So pipeline will help you to reduce the initiation interval of a function or loop by allowing the concurrent execution of operation. Okay. So pipeline function or a loop can process new input every n clock cycle if n is the initiation interval of the loop. Okay, so you for any function you need to find the initiation interval, and that indicates that at after how many clock cycle that new input is taken by that function or by that loop. Okay, so while doing the pipelining, you need to take care of the few things. For example, the loop pipelining, when you are trying to pipeline a loop, can be prevented by loop carry dependency. What do you mean by this? Now I am having the loop, say it is performing 3 iteration, but in the next iteration I am using the data of the previous iteration. That means I cannot initiate the next iteration before I complete the previous iteration, and this means the pipelining will get affected. Okay, so you need to see that how this dependency can be avoided. So you need to modify your code to minimize this or to avoid such dependency so that you can get the best possible pipelining. And what is the best possible pipelining? Your initiation interval is set to 1. For example, you may have the multiple loops. Okay, so you may have the one for loop after the another for loop. So what happens when you apply the pipelining to the upper loop? What happens to the lower loop? When you apply this HLS pipeline pragmas, all the loops in the hierarchy below are automatically unrolled. What do you mean by automatically unrolled? Means all the iterations of the below loop are executed in parallel. Okay, so what do you mean by this? We'll discuss with the suitable example. Okay, so let's have one example where say I have the for loop where I is equal to 0, I is less than 3, I plus plus, and I have the another for loop inside. This is called as a hierarchical for loop where I have j is equal to 0, j is less than 1, and j plus plus. So and then in the inside for loop, what I'm doing the a of I comma j is equal to b of I comma j plus c of I comma j. So when I apply the pipeline for this loop, which is the first loop, then this loop will be unrolled. So what do you mean by unroll? This loop will be replaced by a of I comma 1 is equal to b of I comma 1 plus c of I comma 1, and a of I comma 2 is equal to b of I comma 2 plus c of I comma 2. That means one addition is replaced by the two addition because this both the additions of the internal loop will be executed in parallel. So your loop will be unrolled. In case of the function, as I told you that the our pipelining can be applied to the loops as well as function. So you have the function and you are pipelining that function, but there is a additional sub function in that function. So you are calling some another function in that function. Then you need to make sure that you pipelining that function separately. So you need to add the pipeline pragmas in that sub function, and then you add the pipeline pragmas in the top function. Okay, if you don't add the pipelining pragmas in the below function, that sub function will not be pipeline, and it may affect your performance. You may not get the desired performance. So what is the syntax of this pragma? So you have this pragma HLS pipeline, and these are the options you can mention. Okay, these are the optional thing. One is that you can mention what is your desired initiation interval. By default, it is 1. That is desired is 1, but you can mention anything you want. It should be an integer value. Second, you can mention whether you want to make the pipeline flush enable or you want to make it disable, that you can mention. And you can mention the whether you want to have the rewind kind of pipelining or not. So what is the meaning of these other two one? We'll discuss it in the subsequent slide. So now coming back to the pipeline function. So I'm thinking about pipelining the function. So you can see that when I do the pipeline function, if I'm calling that function say n times, you will see that it is continuously being executed in one after the another in a loop. Okay, so I'm doing the 0, 1, 2 up to n, and then write 0 up to the n. So pipeline function will continuously read new inputs and write new outputs. Okay, so there is no iteration numbers defined in the pipeline function. So when you call the pipeline function, it executes once. When you call it two times, it will execute two times. On the other hand, in case of the pipeline loop, you have the number of iterations. For example, we have the pipeline loop which consists of n iterations. So what will happen? You will have the first iteration, second iteration, third iteration, and the nth iteration. Now your next execution of the loop needs to be started, but this will not be started until you complete the all the operations in the continuous first execution of the loop. Okay, so you have the one execution of the loop. In that you have the n iteration. You need to complete those n iteration before you start the next execution of the loop. Okay, so what will happen in that? You can see that you will get the bubble. What is the bubble? Yeah, during this time you are either not doing the reading or writing operation. Okay, so loop must finish all the operations in the loop before starting the next execution of the loop. Okay, and what will happen? This will lead to the bubble. And what is the bubble here? Here, a bubble is a point where no new inputs are being read. So you can see that the no new inputs are being read as the loop completes the execution of the final iterations. So loop is completing this final task in that particular loop execution, so no new inputs are being read. Or a point where no new outputs are being read when the new loop start executing from the scratch. You can see that initially there will be some time before you get the first output. So that is called as a buffer, during which no new outputs are written as the loop start the new loop iterations. So in case of the function, pipeline runs forever and never ends, as we have seen, while in case of the loop, pipeline executes until all the iterations of the loops are completed. Okay, so this is the issue with the pipeline. And how to avoid this issue? You need to take the rewind options in that pipeline Pragma. So when you enable this rewind option, it enables the overlap of the iteration of successive call to the rewind loop. Okay, so the rewind option is useful only for the pipelining the loop. For pipelining the function, it is not needed. And when you add this option, you can see that the next execution of the loop start immediately. You don't need to wait for the completion of that all the operation in the previous execution of the loop. You can start executing. Okay, this is how you can use the rewind operation. So we have completed rewind, we have completed this one, we know this one, and only thing remaining is this enable flush. Now look at this diagram. So here you can see that I am this is my valid signal, which indicate that the input data is available. Now, during this time, you can see that the valid goes low, which means that the input is not available. Maybe the source which providing the input to me is busy doing some other task, so it is not able to provide me the input. So in that case, what will happen? When the input is not available, that means you don't have the new data process and the pipeline will get stalled. Okay, so you can see that during this time, no operation is happening here. So pipeline continue to execute as long as the data is available at the input of the pipeline. If there is no data available to process, the pipeline will stall. In some cases, it is desirable to have the pipeline that can be emptied or flushed. Okay, so what I want, okay, input is not available, I should not stall. I should complete all the intermediate operation which is going on in the pipeline. Okay, so when pipeline is flushed, so when you enable the flush operation in that pipeline pragmas, the pipeline stop reading the new inputs when the none is available. So you don't have the new inputs, so there is no point in reading as valid signal is low, but you continue the processing. So you don't stop here, you continue all the processing immediately. You don't stop it here, continue the processing. shutting down each pipeline stage. So after some time, what will happen? Your read hardware for the read will not have new data to process, so it will go into the ideal mode. Then comparator hardware will not have any data to process, it will go into the ideal mode. And after some time, write operation hardware will not have any data to write, so it will go complete all its tasks and it will go into the ideal mode. So shutting down each successive stage until the final input has been processed and available at the output in the corresponding output pipeline. Okay. So this is how you can use this HLS pipeline pragma. It's one of the most powerful pragmas available in the HLS. Okay. So one last thing which you need to be careful. So when a function is pipeline, all the loops in the hierarchy below are automatically unrolled. Okay. So last time what we discussed, that when the loop is pipeline, all the loops below are unrolled. Now here I am talking about when you have the function and inside that function you have loop and you applied the pipelining to the corresponding function, then what will happen? The loop will be unrolled. Okay. And when you have the unrolled loop, what will happen? You have all the iterations of the loop are executed in parallel. So that will result in the significant increase in the resource utilization, as well as you need to make sure that all the data needed for the parallel execution of the loop is available at the same time. Okay, so these are the things you need to be very careful. If a loop has a variable bound, for example, you decide the loop, for example, you write something loop which is for I is equal to 1, I is less than n, I plus plus. And this n is your dynamic variable. It cannot be decided at the compile time. So what do you mean by this one? When you unroll the loop, so for example, when I do AI is equal to BI plus CI, and when I say that I'm unrolling the loop, suppose this n is equal to 3, then I need to have the 3 adder. When n is equal to 4, I need to have 4 adder. But since this n is dynamically changing, I don't know how many adders are needed. So I can't decide how much hardware is needed, right? So at the compile time, so how can I build the hardware? So in that case, loop cannot be unrolled. There are few things are there to tell the hardware that okay, this is minimum and maximum value, and based upon that tool can take. But if you don't use anything, then loop cannot be unrolled and your functions will not be pipelined. So you might be applying the HLS pragmas, and if you will see in the warning, it is saying that this function cannot be pipelining, and you will not get the desired result. So you need to make sure that you take care of this issue. One of the last thing is that static variable. Static variables are used to keep the data between the loop iterations, often resulting in the data dependency between the one iteration of the loop to the another iteration of the loop. So in the pipelining, what we are trying to do, we are trying to make the next iteration of the loop to start functioning before the completion of the previous iteration. But if there is a data dependency between the two iterations, we cannot start the next iteration until the data dependency thing is resolved. Okay. So in that case, you may not able to get the initiation interval of 1. You may get the initiation interval of more than 1, because your next iteration will be started only after the completion of the previous iteration. So again, you need to take care of this. You might have to rewrite the code. For example, if I give you the example here, so you can see that here um, I am using this static change variable. That means it is initialized to 0 only in the once in the beginning, and thereafter it will retain the value present in the previous iteration. So you can see that I'm storing the base. If the if condition is satisfied, I'm storing the value in the some memory, and then I'm loading the value. So what do you mean by storing and loading? I'm doing the write operation, which will take more than 1 clock cycle. I'm doing the read operation, which will take more than 1 clock cycle. So that means this function, it will need at least 2 clock cycle. Okay, because it requires a cycle to perform the store operation, and it requires the additional cycle to perform the read operation. So if you pipeline this function, what will happen? You will have the initiation interval of 2, because you need 1 clock cycle to do the store, 1 clock cycle to do the read operation, and because you are going to use that variable in the subsequent iteration of that function, you can't start the next execution of that function before you complete the your previous iteration of the function. Okay, because you are going to modify the change in the next iteration. So unless you complete the load operation and assign it to the y, you can't begin your execution of the next function. How to avoid this? You might have to rewrite the code if possible. So you can see that here we have rewritten the code, and the code is rewritten such that you are performing either read or write operation in every iteration of the loop. You are not doing the both read and write. Since you are not doing the both read and write, you can see that you will get the initiation interval of 1. Okay, so look at this code, understand it carefully, and you will understand that by making these small changes in the code, by avoiding the interdependency between the loop, you can enable the pipelining in the better fashion, so that you get the ideal initiation interval of 1. I can talk a lot of things about the pipelining. There are a lot of videos are available about how to pipeline the digital circuit. If you want to know very basics about the pipelining, how the pipelining is applied in the digital circuit, you can look at the ELD videos which we have shared before. So last 3 lectures are on the pipelining, you can look at, but there are other videos are available. In this topic, in this lecture, I am covering the necessary details for the pipelining which we need for the our lab and in the entire course of the AELD. In the next subsequent lecture, we will discuss about the next HLS pragmas, which is important for our matrix multiplication example.